We're very happy to have as our speaker, Noam Finkelstein, a PhD student in the Department of Computer Science at Johns Hopkins. He's advised by Suchi Saria and also works with Ilya Spitzer on the theory of machine learning and causal inference with applications to biomedical data. And he's going to talk about some of that research today. So Noam, I'll hand it over to you.
Thank you. Thanks very much. Just to clarify, I'm currently advised by Ilya Spitzer. I used to be advised by.
Oh, I'm sorry for I had outdated information.
No problem at all. Just wanted to set the record straight because Ilya's here. Yeah, so thanks for having me. I really appreciate it. I'm looking forward to sharing this work. I've been coming to these talks since I was a master's student in the biostats department a fair number of years ago now, and so it's a privilege to be able to share this research, and I'm looking forward to hearing thoughts from you guys. So feel free to interrupt or ask questions or anything that comes up. So I'm going to be talking about a semi-algebraic view of latent variable causal models with discrete observed data. Hopefully, if it's not already clear what that means, hopefully it'll become clearer as the talk goes on. So the outline of the talk is we're going to start by talking about non-restrictive cardinality bounds on latent variables, move on to talking about causal compatibility as a polynomial satisfiability problem, and wrap up with looking at sharp bounds in really complicated realistic causal models that have things like missingness, measurement error, and so on. And so this work is in collaboration with two groups of collaborators. The first piece is with Ellie Wolf from the Perimeter Institute of Theoretical Physics and Ilya Spitzer. And the second piece is with Guilherme Duarte, Jonathan Mumlo from Princeton, and Dean Knox from UPenn, and again, Ilya, of course. And I just want to note it's been a real pleasure to work with all of these people from different disciplines, different backgrounds, and learn from all their perspectives. Dean and Guilherme are here today, so depending on the kinds of questions you ask, they might field a couple of them. Okay, so the motivation is, realistic data is often extremely messy. We have things like measurement error, we have things like missingness, we have selection bias, and it's really hard to accommodate all those things in a principled way using a lot of existing methods. And so the goal is going to be to present a kind of alternative view, a geometric algebraic view that makes it a little bit easier to integrate some of these obstacles into a causal analysis. So we're going to start by talking about general non-restrictive latent variable cardinalities. The setting that we're in is we have a Bayesian network, script G. Discrete observed variables are going to be W. Latent variables, unrestricted, are going to be U. A distribution over V, which is going to denote all variables, is in the model, script G, if it can be expressed according to the usual DAG factorization. So there's nothing special here. And we say that it's a distribution over the observed variables is in the marginal model of script G if, again, it can be expressed according to the typical DAG factorization once you integrate out all of the unobserved variables. And so x sub v is going to denote a value in the state space of v, and script x is going to denote the state space itself. So that's basically
a clarifying question from Dan Charstein. The latents are unrestricted. The observed are discrete.
Unrestricted. Sorry?
The latent variables are
latents are unrestricted.
Okay, great. Thank you.
Yeah. Latents are unrestricted, observed or discrete. So if we make assumptions about latents, we can end up restricting the marginal model. So let's take a look at a really simple example. In this model, if A and Y have cardinality 10, if we assume U has a small cardinality like 2, we're going to end up limiting the amount of covariance we can see between A and Y after we condition on M. So conditioning on M closes this pathway. And if you can only carry a certain amount of information, a low amount of information will end up restricting this covariance. So as a result, distributions that have high covariance between these two things will be in the marginal model, but we won't see them if we assume that U has cardinality 2. So the resulting model over the observed variables is smaller. So that's a restrictive assumption. So for certain graphs, it's been shown that sufficiently large latent variable cardinalities do not restrict the marginal model if all observed variables are discrete. So the first motivating question is, can we find finite non-restrictive latent variable cardinalities for arbitrary graphs? The approach we're going to take is kind of a geometric view. So suppose that the state space of observed variables is D. In other words, there are only D possible things that the observed variables can do, possible outcomes. So any model for a distribution over those variables has to be a subset of the D-1 simplex. So, the ith element of a vector in the D-1 simplex would denote the probability of the ith possible outcome. And so one approach we can take is, can we use the fact that the marginal model has finite dimension to limit the required cardinality of latent variables? So to do this, we make use of a result from convex geometry called Dory's theorem, due to Dory in 1907. And the theorem says that any point in the convex hull of a set script S in the space Rn can be written as a convex combination of at most m+1 points in script S. So in other words, if we have a set in a finite dimensional space, we can describe any point in the convex hull of that set in a finite number of points. And the question is, can we construct a set script S that represents the part of the model, and we'll formalize that a little bit, that can be affected by a latent variable u? Because if so, we can make the transition to finite u. So our strategy is going to be, given a true distribution P, we'll construct a submodel, script S u P, for a particular latent variable u and a particular distribution P, that necessarily includes P and also includes all distributions that can be obtained by varying u. And then we'll be able to apply Dory's theorem. So how do we do this? Suppose we're given a true distribution over the observed data, PW, and the corresponding parameters of the DAG. So these can be infinite parameters. If we hold constant the distributions over the remaining latent variables and fix the variable we're interested in, let's call it u1 for now, to a specific value xu1 in its state space, then we obtain a distribution. It's not the original distribution, it's a different distribution. It can be expressed like this, which is basically we just don't integrate out xu1 and we just assume u1 is going to be equal to xu1. And we're going to call this distribution p xu1. So let's visualize what this looks like. We have the simplex, we have our model in the simplex. The truth is some point in the model. And if we hold all of the parameters of the distribution, of the true distribution constant, except for u1, and then we set u1 to be equal to x1 u1, then we'll end up with some distribution, a different distribution. We set it to a different value, x2 u1, we'll end up with a different distribution again. A important fact, an interesting fact, is it turns out that the expected value of this object, pxu1, is equal to the original distribution pw. So it's equal to the original distribution over all the observed data. And the reason is kind of trivial. It's just that, by the definition of expectation, you just integrate out pxu1. This piece, which is pxu1, is just the remainder of the expression for the original distribution. And so hopefully it's kind of clear that all you're doing here is taking kind of the observed variables and integrating out all of the latents, which just gets you right back to the original distribution. So let's take another look at a sort of visual view of this. Again, we end up with different specific distributions for different specific values of u1. We're going to call script S up, so script S for this particular latent variable for the distribution p, a set that includes every distribution you can end up with for different values of xu1. So it includes this guy, it includes this guy, it includes every different distribution you can get for different values of xu1. So we're going to denote that script S. It looks kind of like this. And we just saw that the true observed distribution is the expected value of this guy. And so by definition, it's going to be in the convex hull of this guy. Because it's just a convex combination of all of the points in this guy. So this is just that same intuition in words instead of pictures. So we define this set and show that this guy is a subset of this. So the important thing to note about the script S set is that every distribution in this set is in the model. The reason every distribution in the set is in the model is because we're just setting u1 to a specific value xu1, and it's permitted that u1 takes a point mass distribution at xu1. by the model. And so because it's in the model, we know it has to have dimension less than or equal to the dimension of the model. And so this whole set has dimension less than or equal to the dimension of the model. So, it follows from Carathéodory's theorem that the expected value of this thing, which is in its convex hull, and therefore the original true distribution can be expressed as a convex combination of at most d points in this set. So just, I have an easier time with the visual intuition for this, so just to take another look at the visual. Again, this is the truth. This is the set of pxu1 for all possible values in the state space of u1, and the result says that this argument says that the original true distribution is going to be in the convex hull of this thing, which is a subset of the model. Okay. Are there any questions about this? So far, so good.
Yeah, this is great, and we're very happy that you're speaking on this, Noam. This is very clear so far. But you're saying SPU that could be non-convex potentially, at least the way it's drawn there. But otherwise, PW is in the convex hull, and that's what is the convex hull of SPU in this diagram indicated by?
It's not.
Or you just have to imagine it. You should imagine it. Okay, that's fine. That's totally fine.
Imagine the convex hull. Yeah. Sorry about that.
No, that's fine. It's very nice diagrams. Great, thanks.
Cool. Thanks, Michael. Okay, so a sort of consequence of this argument is that the cardinality of any latent variable u can, without loss of generality, be assumed to be the size of the state space of the observed random variables. And again, just to sketch the argument in one place, by Carathéodory's theorem that we looked at earlier, there exist weights W1 through WD and values in the state space of U1, XU11 through XU1D, such that the original distribution, whatever it is in the model, is equal to a convex combination of these distributions, the PXU1 distributions for any permitted observed data distribution in the model. So it follows that the observed data distribution can always be obtained by setting the state space of U1 to be these values, Carathéodory's points, with the distribution, which is the weights in the convex combination. So the theorem is non-constructive, so we're guaranteed that such points exist. We don't know what they are, but the fact that they exist is sufficient to show that U only needs a distribution of cardinality D, or a state space of cardinality D.
So if W is there's a bunch of binary things. Let's say it's 15 binary quantities. So you're saying that the cardinality of the latent variable is 2 to the 15th?
Yes.
Okay.
Okay. So as Dan is pointing out, that's a big number. So let's see if we can do a little better. So it turns out that the size of this number is important for computational reasons down the line. So we use the fact in this proof that every model is a subset of the D-1 simplex to get a dimension. Sometimes the model has lower dimension than the simplex. So this is kind of going to be the first of 2 steps we're going to use to reduce this bound. So let's just illustrate what we mean by that. So as Dan says, if you have binary variables, the size of the state space is 2 to the number of variables. In this case, we have 4 variables, so we're going to get a state space of size 16. So we're going to get a cardinality, non-restrictive cardinality of size 16. However, there are 4 equality constraints in the model. So 2 come from z's independent of m given a, 1 for each value of a, and 2 come from z's independent of y after intervention on m, 1 for each value of m. And the reason this is an observed data constraint is because ym is the distribution of this is identified. So that means the model has dimension 11, so we get a cardinality of 12. So depending on how many equality constraints in the model, this could be a significant reduction. But can we go further? So some of the dimension, yeah.
So, sorry, Noam, a quick question. You're talking about the marginal model having dimension 11, not the model on not the nested model, right? Or do you mean the nested model?
The nested model and the marginal model turn out to have the same dimension.
Oh, you're right. It's only inequality. Inequalities don't matter for dimension. That's right.
Yeah,
Thank you.
right.
Yep.
Yeah. So the dimension of the marginal model, because that's what we're interested in. Right. So the distribution of the latent variable u doesn't touch a few of those dimensions. Sorry, that should be 11. So what do we mean by that? Well, no matter what I do to u, according to this graph, the marginal distribution of z shouldn't change. And likewise, the conditional distribution of m given a shouldn't change. This is kind of an intuition. And so intuitively, there's some things here that we should be able to discount. We shouldn't have to count them when we're figuring out our cardinalities. So how do we formalize that? We're going to use this really nice parameterization due to Evans and Richardson from 2017 called the Mobius Parameterization. And I'm not going to go into a huge amount of detail about it, but the really important thing is that it encodes all of the equality constraints implied by the model. So in other words, the number of parameters is the dimension of the model. And this illustration shows that there's a bijective map between the Mobius parameterization, which is lower dimensional than the simplex, and a space in the simplex. So you can kind of reformulate the model as just a set in the Mobius parameter space, which has the same dimension as the model, which is convenient for us. So this model has 11 Mobius parameters, one for each dimension of the distribution. 3 of these parameters are these guys here. So these are the guys that we said kind of intuitively we don't think that u should touch. So we're going to exclude them, and we'll talk about in a second, give kind of an intuition for why we can do that. So u touches the remaining 8 parameters, so the remaining kind of 8 dimensions of the model, and so we get a non-restrictive cardinality of 9.
Sorry, no, just another quick point about these. So the way you've written these parameters, the second 2 are counterfactual. And so that might be surprising to folks because you were just talking about how this is an observed data model, but this is because they're all identified as well, right?
Yeah, they're all identified. Yeah, so the parameters happen to have a counterfactual interpretation, but they're all functionals of the observed data because they're only identified counterfactuals.
No, I don't really know anything about Mobius stuff, but if a set is, let's say, non-convex in the original simplex kind of space, will also be non-convex in the Mobius space or whatever. This, I guess, does that question make sense?
Yeah, it makes sense. I unfortunately don't know the answer to it. I don't think there's anything special about the Mobius parameters that convexifies non-convex sets in the simple original space.
The Mobius likelihood is not convex in general, which maybe was not Dan's question, I guess.
Yeah,
but
I think the question is about the model, right?
Yeah, no, I don't think so. I don't think it convexifies things.
Yeah. So the answer is I don't think so, but
it seems like it wouldn't be, but I get it. Thank you.
Yep. Thanks, Dan. Okay, so the sort of takeaway here is that we get 11 parameters. 3 of them we can kind of tell by looking at. We'll formalize this in a second that u doesn't affect them, and it sort of has nothing to do with them, and so we get a bound using the cardinality bound using the remaining parameters. I'll just briefly talk about how we figure out which of the Mobius parameters u touches. So each of the Mobius parameters can be written according to this kind of formula. So it's the probability of the event that some set of variables a takes a particular value in their state space, conditional on some set of values b taking a particular value in their state space after intervention on yet a third set of variables. And there's these variables have these sets have kind of a very particular nature according to the Mobius parameterization that doesn't really matter for us. And the proposition says that the Mobius parameter phi I is a function of the distribution of u only if u is not e-separated from ai by bi after deletion of ci. So this is using, in the next slide, we'll look at what e-separation is, but basically it's using standard causal graphical reasoning that lets us think about whether u is going to have an open path to ai after the relevant conditioning and intervention operations.
So no, I'm sorry. Just a quick question about this proposition. If I were trying to explain this to Yuda, for example, Yuda Pro, who doesn't know about e-separation, but he does know about mutilated graphs, which he invented. So could I just tell him mutilate the graph according to the do in that probability, and then check the usual d-separation in that graph?
Exactly. So that's exactly what's on this slide.
Great.
So all that E-separation is so we have two things that are E-separated, conditional on some stuff after deletion of some stuff. So as Ilya was just saying, to think about the deletion of some stuff, all we really have to think about is an intervention on that piece, and then we look at the graph after intervention. So just to recap a little bit, remember each Mobius parameter has this form. One of the Mobius parameters we looked at that we said U shouldn't touch is this one. So if we map that back to this form, AI is just M, BI is the empty set, we're not conditioning on anything, and CI is A, that's the intervention set. So if we start with this graph and we intervene on A, you can see that U is deseparated from MA, which is what appears in the parameter. So U shouldn't have any ability to impact the distribution of MA, and therefore it shouldn't have any ability to impact this parameter. So that's sort of the graphical argument for where this proposition comes from, and yeah, it's exactly what Ilya laid out. So that gets us to the best non-restrictive latent cardinality that we can get that I know of, which is that the cardinality of any latent variable U can, without loss of generality, be assumed to be the size of the set of Mobius parameters that have this property. Okay. So to recap part one, so this isn't the first work that uses a sort of geometric perspective or even Dory's theorem. So we're inspired by the use of Dory's theorem in this work from 2017. That work only applied to kind of a small class of graphs called network form graphs. So we adapted that perspective, generalized it to a place that can accommodate arbitrary graphs. And we then build on the Mobius parameterization to reduce the required cardinality. So this gives us the first non-restrictive latent cardinality for arbitrary graphs. And the kind of importance of this is that, for a long time, analysts, I think, have worried about making assumptions about the state space of latent variables. So this kind of gives a way of saying it's safe to do so if all the observed variables are discrete and you pick a big enough number, and we'll tell you a number that's big enough. Maybe there are lower numbers, we haven't found them yet. Okay, so now we're going to move on to kind of the next part of the talk, which is where we actually use this stuff. So the results in the previous section are of interest in some settings if you're interested in the properties of latent variables. People like information theorists think a lot about that kind of stuff. But from the perspective of our motivation, now we start to get to the payoff. So the reason that we're studying this is that there are important questions about latent variable models that have incomplete answers. So for me, two of those crucial questions are, one is how can we tell if a distribution, if the observed data is compatible with a causal structure? And two is how can we sharply bound causal quantities in complex causal models? So for models that are formulated as semi-algebraic sets, in other words, as sets of polynomial equality and inequality constraints, these problems can be completely solved up to computational feasibility, which is an important caveat, but still. Okay, so once we know all the cardinalities of the observed variables and the latent variables, we can parameterize the graph according to the usual. Yeah.
Sorry, Noam. So you said that if you can express things as these polynomial equations, it's completely solved. But how do you know there's a unique solution?
So you don't necessarily know there's a unique solution. It depends on the problem.
And so does that? But you're still just doing bounds. So like you're saying, this is completely solved. So I don't. Is it because you're doing bounds, or?
Yes. So what you end up. So we'll see in a moment. So for the first question, so we'll get to this in more detail. But for the first question, it's completely solved in the sense of you get an answer which is yes if the observed data distribution is compatible with the causal model, and no if it's not. There's sort of no.
Okay.
There's nothing left to figure out there. In the sense like and the second question, so you get sharp bounds on causal quantity. So in other words, you get as much information about your target of inference as you can possibly get, given the assumptions that you're willing to make. So there's no information left in the data given your assumptions about your target.
the bounds could converge to a point, right?
The bounds could converge to a point. Yeah.
Okay.
Okay.
So I'm just asking this question because it's relevant for Lamar's thesis paper where we had these polynomial equations, but we couldn't show there was a unique solution, and we just did bounds. But the bounds were basically they were equal to each other, but we just couldn't prove that there was a unique solution because there was non-convexity in the problem.
Yeah. So sometimes you can if the bounds are always equal to each other, well, I guess maybe we can
keep going.
More offline. Yeah, no. But yeah, so that's exactly the kind of thing that we're going to be doing here. So once all the cardinalities are known, we can parameterize the graph. There are a finite number of these parameters because all the cardinalities are finite, including for the latent variables. Some of the parameters of a Bayesian network or a DAG parameterization are identified, and some are not. So here we're just going to look at the same graph we were looking at earlier. So the standard parameterization is you take the distribution of each variable conditional on its parents, and parameters that involve u are not going to be identified from observed data. So the marginal of z in this graph and the conditional of m given a are identified from observed data, and the rest involve u. And so because we don't see u, we can't condition on u, so we can't figure out what these parameters are. Nevertheless, unidentified parameters are still subject to constraints due to probability theory. So for one thing, they'll have to be non-negative. And for another thing, all the parameters involved in the same conditional distributions have to sum to 1. And we also have this observed data constraint, which is that all of the distribution of the observed data has to be the marginal implied by all the parameters of the DAG. And it turns out that's kind of all there is. Those are all of the constraints on the unidentified parameters of the DAG, which leads to this result that a distribution is in the model of the latent variable graph if and only if this polynomial system has a solution. So when we say this is a complete solution, it's in the sense that there are lots of methods to figure out whether a distribution is compatible with a causal structure. Some of them use only equality constraints, which means that you might think something doesn't violate any equality constraints. So you might think it's okay, but it turns out it might not be okay for other reasons, like inequality constraints. So you don't get any of those problems with this approach. It's sort of an if and only if. Okay, so that is sort of the payoff in terms of causal compatibility. As a quick example, we'll just look again at this same graph. So we have one constraint of each type here. So this constraint is the observed data constraint. So again, we get to see the observed data distribution, so that's obviously identified. The parameters for the marginal of z are identified, and all the parameters, the remaining parameters which involve either u1 or u2, are not identified. So the remaining parameters, the unidentified parameters, act as the variables in the system, in the polynomial system. And the reason that we kind of want them to be, we want these cardinalities to be small, is that the smaller they are, the fewer of these parameters there are. And the reason that's important is that a lot of the algorithms that operate on these polynomial systems are exponentially slow in the number of parameters. So that's important. Great. So here we have the polynomial system. There's just sort of one constraint of each type to illustrate, but you can kind of imagine what the remaining constraints are. It's relatively straightforward to construct this system from the graph. The first thing you do is you just figure out what the non-restrictive cardinalities of these guys are, and then you find all the parameters, and then you build the constraints. Once you have them, you can run kind of satisfiability algorithms on them, which there's a lot of work on polynomial satisfiability algorithms out there. We can also, without straining too hard, we can use the same idea to get some bounds for single world counterfactual distributions. So single world counterfactual distributions can be expressed in terms of the parameters of the DAG according to the G formula. This is kind of the usual truncated factorization expression. And the only thing this changes is that instead of just seeing if the system is satisfiable, what we're doing now is optimizing a polynomial expression subject to the constraints of the system. So this is a polynomial programming problem. Okay, so far we've kind of seen that we can get a polynomial system that represents these latent variable models, and we can bound some things, but we can't bound everything yet using the usual DAG parameterization. So in the next few slides, I'm going to go through a different parameterization for DAGs that gives us access to more targets of inference and more the ability to express more assumptions. So cross-world targets can't be expressed in terms of the parameters of the DAG. So cross-world targets are things that involve intervention, two or more different interventions on different variables or the same variable. So these are often used in mediation analysis or token causation or actual causation, and as well as in assumptions like monotonicity. And to express these assumptions, we have to know how variables respond to their parents. We need a function from the parents to the variables. And a sort of nice side effect, which we'll see, is that for many graphs, using this kind of functional parameterization yields a simpler polynomial system. Okay. So a structural equations model of a graph, which is probabilistically the same model as the one we've been talking about, posits that each variable in the graph is a deterministic function of its parents as well as some exogenous noise term. So for example, A is a deterministic function of its parent U and the exogenous noise term epsilon A. So we can think of the exogenous noise terms as telling each variable how to respond to its other parents, to its parents that are actually in the graph. So for example, epsilon A we can think of as being a function that maps from the state space of U to the state space of A. So for every value of U, it tells A how to respond. It tells A what its value should be. Because we don't actually care about the latent variable, we don't really care how it responds to its parents, quote unquote. In this case, there are none. And so what we can do is subsume the noise terms for other variables into the latent variable. So we can say really all that U is doing in this graph is representing shared exogenous noise between A and Y. And kind of in the worst case, that's going to be all of the exogenous noise that affects either one of them. And so by doing that, we can reduce the number of random elements in the system from 4, U, A, and Y to just 2, which is U, which determines A and Y as functions of their parents, of their other parents, and epsilon M, which determines M as a function of its parents. So just really quickly, what this means for parameter counts is if we use the DAG parameters, which is the first thing we looked at, the cardinality bound for U is 6. So we get 6 parameters for that distribution, 5 or 6, depending on how you want to count for that distribution, 12 for A given U, 24 for Y given UM. We don't get any for M given A because those are all identified. So they're, for our purposes, in terms of variables in the polynomial system, they're not going to count. So that's 42 parameters. If we use the functional model where epsilon A and epsilon Y are subsumed into U, we get 12. And the reason is there are 4 ways to map between XA and XM, and there are 8 ways to map for U to determine the values of A and Y. Things get a little bit complicated if you have multiple latent variables. So I'm not going to go into all the details on how to find functional models for arbitrary graphs, but we do have an algorithm that can do this. And the algorithm uses heuristics to find functional models that we think will lead to a parameterization with few parameters, because there are many different functional models you can choose in the sense that you can choose to subsume different noise terms into different latent variables, and it will lead to systems with different numbers of parameters. So once you have this kind of functional model, which is beneficial for the two reasons that we just talked about, which is one is you sometimes get fewer parameters, and two is that you get access to these kinds of cross-world probabilities. You can still use the same idea of polynomial expressions. So we denote all of the remaining noise terms that haven't been subsumed as script E. So in this case, that's just epsilon m. And the functional model itself is f. And expressing the observed data constraints is now, just for simplicity to avoid kind of overload, we're just going to use indicators. So if epsilon m and u are such that the functional model says that w deterministically will be xw, then we're going to add a term where we just multiply the probabilities of epsilon m and u together because they're all exogenous. And if not, then this is going to be 0 and we don't add that term. So, I mean, it's not so important to worry about the specifics of this. It's just the point is that we can still express the observed data constraints polynomially, and the non-negativity constraints and the normalization constraints on the exogenous noise terms and the latent variables are going to stay the same as they were before. As I was saying, one of the payoffs is that we can express these cross-world probabilities using the same basic format, which is that, given values for the latent variables and the exogenous noise terms, we get to know what the counterfactual values of every variable are under every possible intervention. So we can evaluate things like, the probability that v under intervention xa is not equal to v under intervention x bar a. Okay, so all of this is going to help us handle really messy data without having to make too many assumptions that we're not comfortable with. So how are we going to handle these complications? The answer is kind of simple. It's really easy to extend this framework to handle messy data by adding constraints to the polynomial system. So once we add the constraints to the polynomial system, getting bounds on targets of inference and also evaluating causal compatibility is going to work the same as it did before. So I'll just run through a few of these kinds of problems that you may end up having to deal with, that we often have to deal with. The first is measurement error. So this is a problem that is important to me. Ilya and I have some other work on this with Roy Adams and Suchi Saria in the CS department, where we look at measurement error in sort of a relatively confined class of graphs. So this work kind of takes a similar idea and extends it to, again, arbitrary graphs. And the basic idea is that often you have variables that are measured with error. In the graph, we denote the unobserved truth with m star and the observed proxy with n. And the error can be random, it can be random noise, or it can be systematic, it can be endogenous for other variables in the system. There are many different reasons that you might end up with error across different domains. Having a graph like this, if we know so we're assuming we know the cardinality of the unobserved truth, and so nothing about finding the functional model for such a graph changes just because one of these is observed and one is not. However, we might want to make additional assumptions. So often people make additional assumptions in the case of measurement error because they have previous research or whatever the case may be to back up those assumptions. A very common one is a bound on the probability of error. So you might assume the probability that the observed proxy does not equal the truth is less than delta. So if you want to apply that assumption, that extra assumption, all you have to do is add a constraint to your polynomial system where the polynomial expression corresponding to this event, which we can get in the same way that we've expressed polynomially the probability of other events, is going to be constrained to be less than or equal to delta. So it's just another inequality constraint. You still end up with a semi-algebraic system. And then the observed data constraints are applied to A, M, and Y. That's A, M, and Y. And so in addition to marginalizing out U, you also have to marginalize out M star. you also end up with missing data. So missing data is a case where you don't observe all of the variables for all of the subjects. And the way that's usually represented graphically is you have a missingness indicator, in this case R, which if R is 0, then the observed proxy for the truth is going to deterministically be question mark. So in other words, if the missingness indicator says you don't see anything, then you don't see anything. All you see is that it's missing. Again, it's relatively straightforward to extend the algorithm for finding functional models to this case. It actually simplifies things because you have a deterministic functional relationship, so you don't have to allow for every possible response of every variable to its parents. This is a slight generalization of the way missingness is normally represented in graphical models, in the sense that it permits proxies to be measured by error, and that's kind of fundamental to this, to the motivation behind this work, which is that you often have many problems at once. And it also permits indicators to be causes of arbitrary other variables in the graph. I'll go through just two more extensions that I think are important for handling realistic messy data. So the first one is selection bias. So this happens when, obviously you only see what you see when you get a sample. And observations may be selected into the sample for reasons that are related to the system under study. So selection might be endogenous. If you ignore this fact, you might end up with inference that's very misleading. So from our perspective, the way that we extend the semi-algebraic approach to deal with this is we say the observed data, what we get to see is now the probability of the observed variables conditional on the selection variables equal to 1. So fortunately, that's still polynomial. So we get to observe this thing. And then these two things, which, this conditional distribution is just equal to, sorry, I got these in the wrong order. It's equal to this divided by this. So imagine these are flipped. These two things can be expressed polynomially, in the same exact way that we expressed everything else polynomially, using the unidentified functional parameters. And so you end up with the polynomial equation on the left and equals a polynomial equation on the right. That's just a polynomial constraint, no problems. And the last scenario that sort of like messy realistic scenario that we want to be able to address, which really I learned about from our collaborators in the political science world, which I guess is one place where this is a prominent issue, is the data fusion problem, which is, sometimes you have access to data from different sources on different things. So there might be a study that only examines a subset of these variables. Maybe you get, an experiment that examines the effect of M star on Y, and then separately you have a study that looks at A and M star, but their selection, and so on and so forth. So you can have these kind of arbitrarily messy problems where you have different distributions from different sources. And the way that we extend the framework to accommodate that problem is the observed data constraints are just applied to each known distribution separately. So it's relatively straightforward. You might also want to incorporate additional assumptions into your model. So a common assumption is monotonicity. This just says, the probability that outcome under a lower treatment, the probability that outcome under a higher treatment is less than outcome under a lower treatment is 0. That's the traditional monotonicity assumption. So the way that you incorporate that is, again, you just add it to the system of equations. You can also incorporate a delta relaxed monotonicity assumption, which is what it sounds like. Instead of insisting that there's nobody in the whole population who experiences a negative effective treatment, you say there's a bound on the proportion of the population that experiences a negative effective treatment. Okay, and so to wrap up, I'm just going to talk about sensitivity analysis in this framework, which I think is important, again, in keeping with the theme of really being careful about allowing for every kind of assumption that we might need, and making realistic assumptions and checking that our inference isn't too sensitive to them. So the first kind of sensitivity analysis you might do is we went through these two assumptions, one about measurement error and one about monotonicity, that we had these kind of delta relaxed assumptions. And one question we might want to ask is, how much can our target vary as we allow delta to take different values? So for example, if we assume that the probability of measurement error is less than 0.5, and we do our inference under that assumption, we might want to see, if we vary it a little bit, if we say it's 0.4 or 0.6, does that substantially change our inference? And if it does, then that means we might want to put a little bit more effort into investigating or finding a solid basis for that assumption. And if it doesn't, it might mean that it doesn't matter so much if we get it exactly right on the measurement error assumption. One that I think is kind of an interesting sensitivity analysis is to the levels of confounding. So we say the fact if y is if u is a cause of y, that means that different values of u might induce different outcomes for y. And so one way that we can test the sensitivity of our inference to confounding is by putting a bound on the proportion of the population for which different values of u will lead interventionally to different outcomes for y. So if this delta is 0, that's equivalent to this edge disappearing. And as it goes up, it means u can have an effect on more and more y values in the population. So we might want to know how much does our target vary as we permit different levels of confounding? And to figure that out, we just try the optimization problem with different levels of delta. Or, and I think this is also kind of an interesting application, we might want to know how much confounding do we need before our distribution is in the model. So for example, if we have a distribution where a and y are not conditionally independent given m, we know that u has to exist to some degree. So if delta is 0, we're going to get a result using the satisfiability approach that the distribution is not in the model. And as delta increases, the level of confounding increases up to a point where the distribution enters the model, or the model sort of permits the distribution. The distribution is not changing, the model is. And that can be kind of an interesting question, which is how much confounding do we need at a minimum to explain this level to explain this distribution. There's sort of a very similar thing you can do to allow for only weak self-censoring, which I'm not going to talk about, I guess, for reasons of time, but it's the same kind of idea. And so just to bring this back to the motivation, really what we set out to do is create a framework where you can accommodate complicated models that have all kinds of problems, and you can bound, in this case, we're bound with sort of somewhat exotic target, which is the probability of causation, the probability that XA causes Y. And the hope is that you don't need too much specialized knowledge to do this. Every step of the process is kind of can be automated. So we can automate figuring out the latent variable cardinalities. We can automate finding the functional models. That means we can automate finding the polynomial system and converting the target of inference into a polynomial and the parameters of the system. So, I just wanted to show this graph again to kind of bring it back to the motivation. This is kind of a similar graph that also maybe you're interested in bounding a cross-world target. In this case, it's a target called the natural direct effect. It's often used in mediation analysis. Okay, there are a number of practical considerations. So even simple models can lead to systems with a lot of variables if you have a lot of unobserved confounding. Branch and bound algorithms. So we have a branch and bound algorithm for polynomial programming that gives you a bound on the tightness of the bounds. So it's like a guarantee that the bounds that it gives you back are only so far from the sharp bounds if it's stopped early, which is kind of one way of helping to get around the computational feasibility problem. And I'll also just mention one aspect of future work that I think is very interesting is, as you've seen, a lot of these systems of equations have a very particular structure. They share a lot of structure between them, and so one thing that we want to look into is whether we can take advantage of that kind of very structured format to come up with faster algorithms than the sort of general polynomial programming or polynomial satisfiability algorithms. Okay, so just to wrap up, using the semi-algebraic approach allows for sharply evaluating causal compatibility and also sharply bounding causal parameters, even in very messy settings. And the reason we care about this is that it opens the door to using more believable models. Even when they prevent identification, you can still get sharp bounds. That's the end of what I have.
Thank you very much, Noam. That was great. So we'll open up the floor for questions.
I think so. Since Dan isn't speaking up, I will just mention that he had a comment in chat about uncertainty quantification, but I'm guessing there is a more basic question, which is inference.
Yeah.
Say anything about that?
So there are, I think, a number of, so we haven't totally resolved the question of uncertainty quantification. In the paper I mentioned with, that Ilya and I worked on with Roy and Suchi, the approach that we take is to use uncertainty bounds on the empirical distribution and incorporate that into the system of equations. And in that paper, it's a linear system. So let's see. If we go back to so if we go back to this idea. So in this, if we're not thinking about statistical uncertainty, we have an exact equality here. So we're saying the observed data distribution is exactly equal to this marginal of the unidentified parameters. If we're thinking about uncertainty, we might say, instead of insisting that the observed data distribution, or that the true parameters marginalize exactly to the observed data distribution, we might only insist that they marginalize to a distribution that's inside of the uncertainty set for the empirical distribution. And if we do that and then run the optimization procedure or the statistical or the satisfiability problem, then we'll end up with valid bounds or sort of valid uncertainty about membership in the model. The problem is that we don't have a really good way of expressing like a sharp uncertainty set for like statistical uncertainty set for the empirical distribution under these various latent variable models. We only have a way of expressing it, a small set under the sort of like under the simplex model. And so, yeah, so we're still working on that. I think there's that, I don't know, I think Dean might still be here. There's another idea that he's been playing with.
Yeah, I think it's a fair summary. That's the one that we know definitely works. The other alternative, so what Noam didn't mention is the way that we solve this problem involves some dual methods where we actually get access to the extreme points, the extreme DGPs. So the other alternative that we're playing with is to actually simulate from those DGPs and do a sort of like a parametric bootstrap inspired technique. And so there are some concerns about like some stuff that Dan raised. Like if there are multiple solutions, we don't know which one would lead to wider intervals and so on. So we're still trying to grapple with those points.
Noam, could you talk a little bit about, so there's some people who, view the world from a discrete lens. So even if like there's no such thing as continuity, continuous random variables, everything's discrete. They have that view of the world. If, some of your variables, let's say age, and age can take on many levels, right? But we think of it as age as just in terms of years, so everything's discrete. And you've got many of these, so your system of equations are still going to grow. How does this thing scale computationally? How can you talk a little bit about that?
Yeah, it scales really badly. Is the short answer.
So I mean, you talk about how this can be used to answer messy questions, problems with complex things, but do you run into a computational bottleneck that makes it, not solvable?
You definitely run into a computational bottleneck that substantially limits the applicability to large problems. And so there are ways around that. So there are a lot of approximation algorithms in real algebraic geometry that we can borrow that help a lot. If you're willing to discretize further, obviously that helps a lot. In systems without a lot of confounding, in other words, like if the parameters that are increasing with the number of levels of the observed variables are identified, then you don't have a problem. So if there's not too much unobserved confounding, then you don't have a problem.
No,
so like for example, if the
Sorry, I interrupted you. Go ahead.
Well, sorry, I was just going to quickly say if the cardinality of z like increases a huge amount, if like z is age, then that's not a problem because the parameters of its distribution are identified, and so they're not going to be variables in the system. So that's sort of a non-issue. So it depends on a lot of things, but certainly it's a serious problem that we have to think more about.
So what I was going to ask about is the follow-up to Dan's question, which is that for certain kinds of calculations with graphs, people had the smart idea that they could systematically exploit equality restrictions, like with some product algorithms and stuff like that. And I noticed that there is some superficial similarity between like computing a small conditional in a large base net with like this kind of equation with sums and stuff that could possibly be pushed in and stuff like that. That's the way those algorithms work. And I do wonder whether we could do something with that to scale to large problems better if the graph is sparse.
Yeah, for sure. And that's exactly the kind of stuff that I want to think more about, is if we can use this sort of special structure of these polynomial equations relative to like arbitrary polynomial equations to speed up those algorithms.
The other like approach that we're taking. Oh, sorry. Go ahead, Noam.
No, please.
Oh, I was going to say, to your point about relaxed or approximate solutions. So it can become difficult to find sharp bounds, but the approach that we're using right now is, like, regardless of how long it would take to find the sharp bounds, the procedure, if run to completion, would ultimately like find the sharp bounds. And so we have a technique. It's a spatial branching bound technique where even if you stop early, it'll give you valid causal bounds that just aren't sharp. And we can actually quantify the maximum extent of the non-sharpness.
Yeah, sorry, that's probably what I should have said. Thanks, Dean.
I just want to say this is very impressive work, Noam. It's you've blown me away with how impressive this is. Thank you very much for presenting it.
Thanks, Michael.
Totally agree. Noam, great work. Very excited about it.
It's very, very kind of you both to say. I appreciate all of your questions and insights. It's been really, like I said at the start, it's a privilege to present to this group after attending talks here and learning from you all for so long.